called. It's supposed to be colors, but colors disappeared at some point. So it's a common work with Nikos Frantzikinakis from the University of Crete. And it's about multiplicative functions, so a function belonging to the domain of number theory, and higher order uniformity. Okay, I will try to define this, not a mathematical definition. Okay, something linked to higher order Fourier analysis. So there is a combinatorial application. So first is the definitions. So multiplicative functions. Then the classical definition. So a function is supposed to be defined on the integers and with complex values. And it is multiplicative if chi of xy is the product chi of x chi of y whenever x and y are relatively prime. And when it is true for all xy, then we say that the function is completely multiplicative. So M, purely M is a family of multiplicative function of modulus n-1 in this talk. For example, one of the most classical multiplicative function is a Möbius function, which is defined that mu of n is, there are two cases. If n is square free, that is a product of distinct primes, then mu of n is -1 to the power k, the number of distinct primes. And in all other cases, it's 0. It's multiplicative. So there are other classical functions that are completely multiplicative. I don't define. UV function, Dirichlet characters. And a very simple one, that's a function, perhaps I had to begin with this one. N is a variable, t is a parameter. Okay? N to the power it is a multiplicative, is completely multiplicative function. Okay. Then the motivation. We began with a problem, a purely combinatorial problem. And we try to translate it using machinery, Furstenberg correspondence principle, and so on. And we arrived to a problem involving multiplicative functions. And also this linked to questions, it's not exactly Schroeder's conjecture, but linked to Schroeder's conjecture. So I have to explain the notation. The E, big E, means average. And n between bracket, capital N between bracket, is the interval 1 to n in the integers. So this expression here is, here perhaps? Yes, means 1 over n squared, sum for n is equals 1 to n, and so on. So L1, Lk are supposed to be perhaps distinct integers. It will be perfect. And we want to understand these averages. And the first point is to see whether these quantities are continuous with respect to some or to some other norm, so that we can make approximation, some kind of analysis. And the good norm for this kind of problem is, the good norms are the Goer's norms. Okay, I define them later, but the important here is that this average for different functions, even if it's not the same, but bounded by 1, is bounded by some expression depending on the Goer's norm of phi1 or phi2 and so on. Okay, and so then this one. So then, because we know that the Goer's norm is an important norm for the evaluation of these averages, then so we have two kinds of problems. The first one is the following: distinguish between good and bad multiplicative functions. Good multiplicative functions which will be uniform ones. Uniform ones in respect to the Goer's norm here. Okay? If this Goer's norm goes to 0 when n goes to infinity, then the average here, the star, converges to 0 when n goes to infinity. And of course, we want some condition which is manageable. Okay, it's not the condition. The function is uniform if and only if it is uniform. I need something that we can check. Okay, and the second problem is the following: for many multiplicative functions, the first condition doesn't hold. For example, for Dirichlet characters or n to the power it and so on, then we want to separate the multiplicative function as a sum of two objects. One object containing the information, which means as a good structure we can deal with, we can make computations, because it has a good structure. And the second term, which is a uniform, means structured, and un means uniform, okay? And the second part is uniform, meaning it has no or small contribution to the averages. So the Goer's norm is small. And for combinatorial application, there is a difficult point, that is we need to do that uniformly. That is for all multiplicative functions simultaneous. Okay. It's not the same problem as considering one single multiplicative function and trying to prove things about it. But we need uniform estimates. Oh, no signal.
Okay.
Hi.
The computer off.
Oh, yes, I know. Yes. Okay, okay. Perhaps I change the pages here so that so Goer's norm. I believe that almost everybody here knows Goer's norms. So they are defined inductively. And here you see that. What?
Define them carefully.
Yeah.
Carefully, okay.
Not everybody knows.
So one remark is that here, by a magic, the interval 1n disappeared, and here we have a cyclic group Zn. It's easier for the computations. Okay. Then the first Goer's norm is not a norm. It's simply the absolute value of the average. Okay, it's subadditive, but okay, some non-zero function can have zero Goer's norm number 1. But it is only defined in order to begin the induction. And the Goer's norms are defined inductively by this strange formula. Well, perhaps I omit the U2, the line below here. Okay, because here is a closed formula for the U2 that is obtained by the induction for S is equal to 1. Then we see that there are 4 terms that we take the product of the function at 4 points, making a parallelogram. Okay, some kind of parallelogram. And so there are some complex conjugacy, but forget them for the moment. And we take the average. And it's not so obvious that this average is non-negative, and in fact positive, except if the function is 0. Okay, and we take the norms, the power 1/4 of this average, and it's not completely obvious that it is subadditive, but it is. For it will be clear on the next slide. So and so on. The norms are defined inductively. So one remark. So the definition: a function is US uniform. It's not a mathematical definition. Okay, a function is US uniform. If its US norm is small. What I mean by small? Everywhere in this talk there is a parameter capital N, okay, which is implicit. So this talk is about finite objects, finite averages, but of course I want all the estimates to be uniform in N. When I say that something is small, it means that it is bounded independently of N, or perhaps that it tends to 0 when N goes to infinity. Okay. So then the norms increase, and US plus 1 uniformity is stronger than US uniformity. So for example, the U2 norm, so I use the classical notation for the complex exponential, and I recall the definition of the Fourier coefficients on a function defined on Zn, of the cyclic group. Okay, I don't read. And it happens that the U2 norm is simply the L4 norm of the Fourier transform. Okay, you can check that immediately on the definition, on the formula. Okay, and so the conclusion is you have immediately, because you are mostly interested in functions that are bounded by 1. And for a function bounded by 1, the L2 norm is bounded by 1 also, and using Parseval, then you have these bounds, lower and upper bounds. Then the U2 norm is comparable to the supremum of the Fourier coefficients. Okay, for functions that are bounded by 1. A function is Fourier uniform, but Fourier uniform means has small Fourier coefficients, if and only if it is U2 uniform. And at this level, it's clear. But the U3 norm and the US norm for S greater than 2 do not share this kind of properties. First, you cannot express them easily in terms in the Fourier coefficients, okay? And you don't have a comparison like this one. For example, the U3 norm is self-dual. Up to a normalization, the U3 norm of a function is the same as the U3 norm of the Fourier transform. Then taking the Fourier transform doesn't help. Okay, you get the same result. Okay. So here, we identify the interval 1n with the cyclic group Zn. Of course, this is not completely correct because the addition in Z over Zn is not the same as the addition in the integers. So in all the statements, there is a mistake of this talk because I confuse. Okay, you have to make some simple but boring technicalities in order to compare. Okay, but so in this talk, please forget that the additions are not the same. Okay. So for S is equal to 2, then as explained before, our estimates are estimates about the Fourier coefficients. Then we want estimates about the Fourier coefficients of multiplicative functions. And a good tool is a lemma by Katai. There are other methods, but a very good tool is a lemma by Katai of 86. First, it was rediscovered independently, apparently, by Bourgain-Sarnak and Ziegler. They call that a finite version of the Vinogradov method, and only for the Möbius, but in fact it's general. So perhaps I read from the bottom to the top. Suppose that you want to show that a multiplicative function chi is orthogonal to some function f, or more precisely, that some function f is orthogonal to all multiplicative functions. Then it suffices to prove that the function f has small self-correlations, but not ordinary correlation when you take a function and you translate, but multiplicative correlations. It means that you take your function, you delete it by two different numbers, prime numbers, and you look at the correlations. Okay? Then, I don't know if it is needed to read it. Okay? Then, here, of course, this bound is because I want the function is defined only until n, so I can take the only here. This is the correlation of f dilated by p with f dilated by p prime. Okay. Then if this one is smaller than delta, but obviously we cannot impose that for all p and p prime. That for p and p prime less than something, k. Okay, then you win. You have a correlation of f, which is small with every multiplicative function. So what is important here? First, that nothing depends on the multiplicative function, of course. Okay, nothing depends on n. Yes. Okay, k and delta depend only on epsilon. Okay. It is not a difficult lemma. Okay, it's what's the name? Elementary number theory. So, and we can use this lemma in order to describe the Fourier coefficients of a multiplicative function. And these coefficients are small on minor arc. What I mean, minor arc, psi of n here, the Fourier transform is taken here, which are far away, or relatively far away, of every rational with a small denominator. Okay. Then again, if I read it in the converse direction, the contraposite, if a multiplicative function has some large Fourier coefficient at some point psi, then it means that psi over n is close, is not so different of a rational with a denominator q. Okay? So the bound dependence n is important, and q is depends on nothing, okay? Only on theta. And a limit version of that is limit when n goes to infinity and so on, is an old result by Debussy and Delange. Or Debussy or Delange. It's not clear. And or. Okay. So now for arbitrary S, because it's the title, the talk. Then recall that our first problem was find soft conditions such that a multiplicative functions has a small Gauss norm US. Or that the norm US on the interval n goes to 0 when n goes to infinity. And there is a result proved in several steps, Green-Tau and then Green-Tau-Ziegler in 12, that the Möbius function satisfies this condition. Okay, and some other function like that satisfy this condition, the Liouville function, but not the Dirichlet characters and not n to a complex power. So, and we have a good, simple characterizations of these multiplicative functions. We call them aperiodic. It will be apparent here why. So then for a multiplicative function, we have several equivalent conditions. Let us concentrate on the first and last one. The first one explains why I call that aperiodic. If you average this multiplicative function on an infinite progression, then I find 0. Okay, this is the first condition. The last condition is that the US, exactly what we want, the function is US uniform. Okay, then the second condition is linked to the first one by Fourier analysis, Fourier coefficients, and the third one is equivalent to the second one by using a classical result of Halash. I will comment a bit of three. In the language of Granville and Sunda, please.
Sound.
Yes. If they say that a function like that does not pretend to be the product of a Dirichlet character and to the IT. Okay. Then it's relatively classical, and it's some kind of smooth condition. Why? If you want to define a completely multiplicative function, you have only to say what are the values on the primes. Then a completely multiplicative function is completely defined. Okay, it's equivalent by these values. Then here we have a simple test on these values. Okay. So the implication, so the 0.4 for S is equal to 2 is also Fourier analysis, but for S greater than 2, then we need machinery, heavy machinery. Okay. Then, again. Yes, yes, please. So, for aperiodic multiplicative functions, you have something which is more or less related to Scholas's conjecture. We say that if you have a polynomial of two variables, two integer variables, with one quadratic term to some power r, and a product of linear forms, plus some conditions, okay? Then if you take a multiplicative function, it takes average, then the average goes to 0 when n goes to infinity. So here you have two things. First, there's a quadratic term here, and to deal with this quadratic term, we need a Halash, but Katai result, but not in the integers. Instead of primes, we use primes in the gauche integers and so on. So it's a variation, okay? But it is not really the most difficult point. The important point here is that we have these not for a single multiplicative function, but for a whole class of multiplicative function, which is described by easy conditions.
What is aperiodic?
Aperiodic is satisfying one, so it's written somewhere? No, it's not written. So under this condition, I say that the multiplicative function is aperiodic. The word is perhaps not the best one, the terminology, but okay. So even for this one, we need the strong result of decomposition. We cannot stay inside the family of aperiodic multiplicative functions, even for this one. So the main result is, it was my second goal, to decompose every multiplicative function as a regular part and structured part and a uniform part. And this is given by the next result, and there are some quantifiers a bit, and the result SCT is not correct because I removed some quantifiers and so on. Okay, then it's an approximation. Okay, and even if that is not strong enough for our needs, we need something stronger. But it's sufficient because it's sufficiently complicated like that. So then given epsilon positive epsilon, then every multiplicative function can be decomposed as announced and a structured form function and a uniform function. First, uniform bound. A structured function is bounded by 1 in absolute value. Okay. But it is structured and it has several meanings. So it is a trigonometric polynomial with a bounded number of coefficients in this. And bounded means depending only on this epsilon here. Okay, and we know the spectrum. Spectrum also depends only on epsilon. Okay. It is approximatively periodic. Not periodic, but approximatively. So there is one Q, okay, so that's a structured function translated by Q is essentially very close to the function itself. Okay, then Q as well as the other constants do not depend on n on the multiplicative function. Okay, and the rest is just uniform. Okay, uniform. The US norm is less than epsilon. So this is a bit technical result, but okay, it was the result that we needed for. Please. Yes.
The decomposition does not depend on the n.
On the n, oh yes, it's a subtlety. For each n, I have a decomposition, but even I look at the function in a larger interval, then the decomposition can change. Yes, it's not a decomposition. There is no result like that. It's impossible. For example, it's rare.
So what means approximately periodic? What is the small q?
Small q depends only on. Q depends only on the epsilon.
Not on b.
Okay, nothing else. Okay. But why? It's one of the difficulties. There are multiplicative functions without averages. That is, the averages from 1 to n does not converge to a limit. Okay, when n goes to infinity. Okay, then in that case, it will be impossible to have a decomposition like that, which is valid on the whole integers. Then the part, uniform part, and the structured part are defined for every n, but change with n. Then our results are results on the finite level. Okay, even if it's asymptotic, what we want are control on the asymptotic. Okay, then a strategy. So we use a lot of machinery coming from the papers, different papers of Grintau and Ziegler and so on, but for the Möbius functions. Okay, then, but we cannot simply take this result as black box because your functions are not uniform, are not the Möbius. We cannot use arithmetic properties of the Möbius function. You have to start from the beginning, from nothing, almost nothing. But you can use a lot of machinery, of course. So then the idea is first to prove the result for S is equal to 2, that's a U2 norm. That's a pure result, of pure Fourier analysis. Then it's done by our estimates before on the Fourier coefficients on the minor arcs. And we can decompose any function here, multiplicative, as a sum, the kind of sum we want. But unfortunately, we don't have that the uniform part is small in the US norm. It's only small in the U2 norm, okay? And our method is to prove that, in fact, so that we have a good description of this decomposition, explicit more or less. We have to prove that this uniform part is really uniform, it's US uniform. That is completely, it is not true for an arbitrary function. I have to insist. Okay, we use at all the steps the fact that the function is multiplicative. Because for an arbitrary function, it's false. Okay. Then on the side, I proceed by backwards, okay, by reduction. And one technical difficulty is that the structured part is present at all the steps. Okay. For the Möbius function, for example, there is no structured part at all, and it's much more simple. So then we'll use the inverse theorem by Grintau, and Ziegler. Okay, I need some definitions. Okay. It's a bit too fast for people which are completely outside the subject, and a bit too long for people inside the subject. It's difficult, okay, to find a way. So if G is a S step, so for S equal 2, for example, two-step nilpotent Lie group and gamma a discrete compact subgroup. For example, SG is a group of upper triangular matrices with one of the diagonal. It's called 3-3 matrices. It's called the Heisenberg group. No, of course. Okay, and gamma is a group, the subgroup of matrices with integers and trees, and this one is a Heisenberg group, and you have this expression, and then X is a compact manifold, okay, and so we choose some element of the group and some regular function on X, on the homogeneous space, and we evaluate the function phi along the orbit. Okay? Regular function is not important, but at least deep sheets. But if you want to see infinity, you can change absolutely nothing. And so there is a very difficult theorem of Grintau and Ziegler, which interprets the Gower's norms in terms of nil sequence like that. A nil sequence is, okay, a function phi, no signal yet, a function phi, okay, evaluated along an orbit. Then this theorem, before to read it, we have comment, is the best analog that we can have for the Parseval formula. The Parseval formula explains, computes the L2 norm of a function by comparison with Fourier coefficients. And here we don't have Fourier coefficients, but you have a weaker form and more intricate form, similar form. Okay. Then for every epsilon, S is given. Okay. There exists a Lie manifold, S minus 1 step Lie manifold, and a constant theta, everything depending on epsilon, with the following properties. If a function f of modulus bounded by 1 has a Gower's norm greater than epsilon, then it correlates with a nil sequence. It correlates, that is, it has a correlation greater than theta with some nil sequence defined as above on this manifold X. If a function as defined on the torus as bounded by 1, okay, as a L2 norm which is not too small, then it has a correlation with some complex exponential. Okay? If a function defined, a sequence defined on z over in z or zn as a Gower's norm, not too small, then it correlates with any sequence. So recall, our goal was to prove that this uniform part is really uniform, small s1 norm. Then we are reduced to prove this one. Okay, that if phi is a Lipschitz function defined on nil manifold X as above, and then the correlation between the uniform part of chi with this nil sequence phi of G and gamma is small. Okay, then now we are arriving to dynamics. Okay, because this one is an orbit. Of course, it's a small, not small, finite portion of an orbit. So it's a dynamics along finite orbit. Some people would prefer perhaps continuous flows instead of discrete time flows, but okay, here it will be an exponential flow. Okay, it's more or less the same. Okay. It will be an orbit on a finite, continuous orbit, but for a finite time. So, then for the Fourier method, for the U2 norm, we use minor arc estimates. What is the analog of a minor arc estimate? Okay, then the notion is a notion of totally delta equidistributed sequence. I don't give the definition. Okay, but I make a parallel with the case of the torus. If you consider a finite sequence, not an infinite sequence, a finite sequence, and assume okay, it is well equidistributed in T. I don't define. The discrepancy is small. Okay, the discrepancy is small. Okay, it's a good distribution in the torus. Then it means that alpha is not too close to a rational with small denominator. Okay, and immediately I make two remarks. T and TR. Okay, there is you can translate that in TR instead of T, up to some obvious modifications, and a result like that holds for polynomials. Okay, I don't write the condition precisely, but if a sequence like that is really irrational, then it has a good distribution on the circle. But remember, it's a finite distribution. Okay, the results are much simpler in the infinite case. So we use now another theorem of Green-Tao, which is a theorem of decomposition of finite sequences defined on nil manifolds. So polynomial I explain later because I need polynomials. But for the moment, your sequence can be decomposed as a product of a periodic sequence, a sequence with a few variations, and a polynomial sequence that is well equidistributed. So, a sequence in TR, finite sequence, you can decompose it as periodic one, plus a sequence that moves very slowly, okay, and a sequence which is random. But random in a submanifold, in a subtorus, okay, in a limit. This is a complete analog. And why polynomials? Because that's the problem in the non-abelian case. If we start with a linear sequence like that, linear means G to an element G to a linear power of n, G to the n. Then at some point in this procedure, we find polynomial sequences. It's a polynomial like that. H1 to the n, H2 to the n square, and so on, with a degree bounded by the parameters of the problem. Okay. No, we use this factorization, and we know that we have we know exactly, we have an explicit construction of the decomposition, and we are reduced to prove this theorem, which is the minor arc estimate corresponding to the abelian minor arc estimate, which is the following. Okay, if I have a totally equidistributed nil sequence. I mean that you have a sequence in a, we have a nil manifold, a sequence, polynomial linear g to the n if you want, okay, which is totally equidistributed in x, and you have a function phi which is Lipschitz and of 0 average, and then, okay, phi is the nil sequence corresponding to this function phi has a small correlation to with every multiplicative function. So now at this point, we have the following. We wanted to prove that the uniform part of an arbitrary multiplicative function has a small correlation with any nil sequence. And we have something which is completely the reversal. We have the multiplicative function here instead of the uniform part, but here we have a nil sequence which is uniformly equidistributed, totally delta equidistributed. Okay. So at this point, we use Katai lemma, and we are arrive backwards to this problem. We have to prove this theorem, and the important remark is that there is no multiplicative function here. Okay, we completely killed the multiplicative function. We have a problem about the orbits in a nil manifold. Okay, then consider a nil manifold. I start from the bottom. And you have a sequence. That's g to the pn, and this is g to the p prime n, if you want. Okay, then it means that you have two orbits, and you have an orbit in a nil manifold, and you take the same orbit at two different speeds. Okay, the first one is at speed p, and the second one is just p prime. And so look at the distribution of this guy in the product, in the Cartesian square. Okay. Then the idea is that if we have this solution, and if phi is Lipschitz of 0 integral and so on, and if g is totally equidistributed, this thing is small. Okay. And we are reduced to prove that. So I have to. At the end, we have to describe this orbit. Okay? Try to explain that. So the details are not important at this. And it's written somewhere that these orbits are simple, but this claim is false. These orbits, a lot of different possibilities can occur. Okay, it's not so easy. But the important point is that generally this orbit in the square distributes in a reasonable submanifold of the square, not too small. Okay, it doesn't shrink on the diagonal. That's some kind of diagonal. It's very important. Okay, then in all this argument, the main ingredients are the Minorca estimate and this result of distributions. And this is the difference between this problem and the method of Green and Tau. So an application to partition regularity, this will be easier, I hope. So you are given a polynomial function, but polynomial of 3 variables, of 3 integers variables. I write them x, y, and lambda because they don't have the same rule. And we say that the equation P of x, y, lambda is partition regular if for every finite partition of the integers, we can find x, y in the same atom, and lambda arbitrary, well, it's a bit strange, so that P of x, y, lambda P of x is equal to 0. Okay? Then here are, below there are very classical examples. These, some of them, the oldest one is missing, but doesn't matter. And for example, x minus y is equal to lambda square. There's a very classical result of Sarkozy. Okay, then it's clear. If you have a partition of the integers, finite partition, that you can find x and y, we say in the same color. Okay, the atom of the partition is called a color. we can find x and y in the same color, such that the difference is a square. Okay, then this polynomial theorem, van der Waals theorem by Bergelson and Neumann gives many examples like that, which are translation invariant. Okay, by translation invariant, the important variable is x and y, so we can translate everything. So there is an example which is not translation invariant, which is much more recent, by Kalfala and Semeredi. X plus y equals, it's much more difficult also. X plus y is a square. You can find x and y of the same color, so that the sum is a square. And all the other examples I know are either translation invariant or linear in x and y, like this one. Okay, or both. Again. So our results are the following. This is very strange how this works for two equations. So 16x squared plus 9y squared is a square. This is an equation. The other one is x squared plus y squared minus xy is a square. These equations are partition regular. We have a lot of whole class, but I don't write. There is a characterization of the quadratic equation that you can deal with, but I don't give this characterization here. We have an infinity many, and you have a characterization of the equation that you can solve. Okay, so we have a few equations of degree 3, but we don't have a good characterization. We find each example by using a computer program. Then a bit strange. Okay, that we don't have a.
You see, you have a if condition for a quadratic
No,
form?
but for our method to work. Yes, for example, the last line. Okay, for the equation which are here, this one is a very classical problem, old problem. This one also is a problem. Then our method doesn't work, but we cannot conclude. Okay, so it's no. This one is classical problem. The first one. So why can we solve this case? Because we have a good parameterization of the solution. If you take an arbitrary k, m, n, which are integers, if you define x to be k, m, n plus 3n, and y to be k, k, m plus n, m minus 3n, then for some lambda that I don't read, we have a solution. Okay. But we need parameterization of this kind. So this is our condition. So in this kind of problem, it's very difficult to prove that an equation has a solution. And to prove that when I make a partition, then a classical method is to prove the same result but in density. If a set of integers is large, then it contains a configuration. Okay, large to be defined. A classical notion of line is the additive density, but it apparently doesn't work. Okay, then we use multiplicative density. Okay, what is multiplicative density? I don't define it. Classical density is of a set is defined by taking the intersection of the set with the interval 1 to n in the integers, to count, to divide, and to take the limit when n goes to infinity. But here, instead of the interval 1n, we use some kind of multiplicative interval. Okay, so the divider of factorial n or something. Okay, which is a multiplicative Fourier sequence. It's a sequence that you can use to prove that the multiplicative natural number, the semigroup is amenable. Okay, and it is subadditive, the density. Then if, I repeat, if we have a partition of the integers in finitely many colors, then one of the colors must have a positive density. Then if we prove this theorem here, we win. Okay, each set of positive multiplicative density contains a configuration of the given type. So, because I have to make a bit of ergodic theory, it's the title of the program, dynamics, then we can translate this last theorem in ergodic theory. This is not a solution. Each theorem is equivalent to the other. And the deduction is in both directions follows from the correspondence principle of Fürstenberg. But okay, we can prove either one or the other. So then multiplicative measure preserving action of the integers on the probability space x nu is a family of measurable measure preserving transformation of x, which is an action of the semigroup. Okay, multiplicative Tm composed with Tn is equal to Tmn for every m and n. Okay, and we have a Mercodic formulation. If we have a multiplicative measure preserving action of n on a probability space, if a subset of x as measurable subset of x as positive measure, then there exists distinct m and n and some lambda such that m, x and y is a solution of our system. Okay, 16m squared plus 9y squared is 1 squared.
Y is n.
Oh, it's probably n. Yes, here. That's n. And the measure of this intersection are intersected Tn inverse of A, intersected with the Tm inverse of A as positive measure. Okay. So y is equal to, yes, n. Well, how do we obtain this result of partition regularity from our study of multiplicative functions? First, we use this parametrization here. And what we show is that we have many solutions. So for many pairs Mn, then, okay, there are many values of k. Such that x and y belongs to E. Recall that E is a set of positive density, okay, multiplicative density. But many is not the same as many. The first many is additive. It's the ordinary density in A square. And the second many for k, is multiplicative density. And how do we prove that? We make Fourier analysis. But instead of using additive Fourier analysis, we use multiplicative Fourier analysis. What is the meaning of that? Instead of considering an interval 1n, we consider the set of divisor of factorial capital N, for example. Okay? And instead of using complex exponentials, we use multiplicative functions, which are multiplicative characters in some sense. Okay? And we develop our functions using this basis, and it allows us to make computations. But the point is that we cannot consider each multiplicative function separately. In the same way, if we use Fourier transform, we cannot use properties of some multiplicative, some character, some complex exponential, which are not true for another. You know, we use all those coefficients. And here we need to consider simultaneously all the multiplicative functions. It's the reason for which in the preceding theorem, in the decomposition theorem, we need something uniform or almost uniform. Okay. Then we use the decomposition theorem and a stronger, not exactly this one. Okay. And it's the engine of the proof. We plug this decomposition theorem into this Fourier analysis. And there is a lot of epsilon delta machinery, and we win. Okay.
So any questions for Bernhard? So it was a bit mysterious. For some quadratic equation it works, and for others it doesn't.
Yes, it remains mysterious for us. Yes. If perhaps the two counterexamples are impossible for different reasons. This one, so there is a classical parametrization of the Pythagorean triples, but it doesn't fit our need. It's not of the same type, and we believe that at some point we will manage to do this one, because it seems to be only a technical problem. It has a parametrization, but not exactly the good one. But this one, nobody knows how to have a good parameterization of the solution? I don't know. Okay, the reasons are different.
Is it easier when the quadratic form is non-definite? When you have minus.
Yes, we need that solutions like that, of course.
But is it easier, this kind of question, when the quadratic form is non-definite? Like
Yes, I
minus.
need it. No, I need it's more difficult. Yes, I believe it's more difficult because parameterization like that, if with the minus, it's not so clear. It's not so clear. At some point, we use that the discriminant, some discriminant is negative. So I believe that our method is, but I'm not completely sure.
Any other questions? Okay, so let's see.